Hello, and welcome to nanoHUB-U's course on organic electronic devices. My name is Brian Baduris, and I'm in the School of Chemical Engineering here at Purdue University. What I'd like to tell you about today is a scientific overview of a very exciting class of materials and devices that are based not on inorganic systems, but on carbon systems. And what I'd like to cover in this class is how we can design these carbon-based materials to have specific chemical functionality, specific nanostructures, and specific molecular transport properties such that they can be used in organic electronic devices such as photovoltaics, thermoelectrics, and light-emitting diodes. Okay? But these are new, and they're carbon-based materials, and traditionally when we think of carbon-based materials, one of the most commercially relevant ones is the class known as polymers or plastics, and we're very familiar with these. For instance, you can think every day of a time where you've used a plastic bag. Okay? So here we have a nice blue one. We know that we can change its color based on the dye, we can change its strength based on how we process it, and we can change its shape based on the mold. And this material here is an excellent barrier material. In fact, it's so good that sometimes we use them as containers, whether they be plastic cups or plastic bottles for water or soft drinks. We can change the material's properties of polymers such that they can not just be soft and moldable, but also strong and serve as building blocks, or to be very thin so that they can be processed into large rolls and you can see that they're very thin sheets. So the benefits of polymers is that you can change the molecular and processing conditions such that you can tune how they behave in a barrier sense. And traditionally, polymers have been used as barrier materials in a lot of different applications. And we're common and we're familiar with those, and we've used billions of tons of polymer throughout the time that they've been around. Okay? Over the past 30 years, how this has changed is now we've been using organic materials in electronic devices. Okay? And some examples of these include flexible field effect transistor arrays, flexible blue emitting diodes, white light emitting diodes. You can see here from GE Research that we have a white light emitting diode that has illuminated the older technology of the Chinese lantern. You can also have something akin to a flexible television or a thin film television that's emitting many colors. Or you can use energy, or you can harvest energy to make electricity. And what we see here is a very thin film solar cell that's being processed in a roll-to-roll manner. And you can see that in 2004, these devices were roughly 3 inches in thickness. Nowadays, you can actually find commercial products where they can either be used to harvest power off a laptop bag or on top of a surface that's curved here, as we can see on this bus stop right here. And we'll talk about light-emitting devices and solar cells in this class. And we'll also talk about flexible memory devices made out of polymers that you see in this last slide here. And the benefits of all these materials is that if you can combine a source that has a logic display, such as memory, with a readout display, such as the LED, with something that can harvest power, harvest energy, and convert it into power, then you have the makings of something that could have a completely portable display that's flexible and bendable, so you can think of a material that's a foldable tablet. And this all happens because we can tune and design the molecular properties of new polymers that go beyond this barrier polymer paradigm. Okay? So how do we want to think about these organic electronic materials? Okay? Well, they come in two general flavors. The first is that of small molecule semiconductors. And if you recall from general chemistry class, generally when you have a carbon-carbon bond, we'll draw it as a bond between one point of this hexagon to the other point of the hexagon. And this is a carbon-carbon single bond. Okay? We'll also have double bonds, which we'll draw as two parallel lines. And you'll notice in all of these materials that I show here that these bonds alternate between a single line and a double line. So we have an alternating single-double bond. And this is called pi conjugation. Okay? And you'll notice in all of these materials we have a large degree of pi conjugation. And this is how we have delocalization of electrons and thus charge transport. One thing you'll note, if you're familiar with traditional inorganic semiconductors, is that our materials can either be p-type or n-type. And when we say p-type, we mean they transport holes preferentially, or n-type, they can transport electrons preferentially. and how we design these molecules will allow us to know which one is which. And we'll cover that in this course. The second class of organic semiconductors that we'll focus on here is that of polymeric semiconductors. And in these materials, we can either have polymers that serve as conducting materials, like this P.PSS term, or as low bandgap absorbers that are used very frequently in organic solar cells and have organic solar cell efficiencies that approach 10%. Now, how we design these materials very greatly affects how these materials operate in devices, but also how we process these and how we control the nanostructure will impact their device performance. Okay. So one quick example that we'd like to talk about is that of white light emitting diodes. So here we see a laboratory experiment. We have a set of white light emitting diodes, all producing a nice bright color. And the reason they can produce that nice bright color is because instead of blocking part of the light or not allowing some of the light to go through, they actually emit the light. We tune the molecular properties of that white light such that we can have different shades of white light. We can either have the bright white light there, or if you're at home and would like a more candle-like feel, we can also make it more of an incandescent white, as you see on the fins of this fan right here. You'll note that these materials, because they're built on flexible, bendable substrates, can be incorporated into many different form factors. Okay. Here we see how we have a nice overhang of materials, and we can even use them into very flexible materials, as this sculpture represents right here. So here we've taken electrical energy, passed it through our conjugated materials, and used it to emit light. The opposite of this, obviously, would be to take light and then convert it into electricity. And that's the general operating mechanism of a photovoltaic device. And in fact, organic photovoltaic devices are becoming more and more popular and are approaching commercial viability. The way that these devices work is that we have two metals, an anode and a cathode, and in between them we have our polymeric or organic species. And if you recall from solid-state physics, a device output curve for an organic solar, or for any kind of solar cell, looks very much like this, where you have some kind of diode behavior in the dark where you don't pass current, and then as you apply a voltage, the current increases. And when you shine light on the device, you have some kind of photocurrent here. So we have a photocurrent, and this is the difference between when the light's on and when the light's off with no applied bias. Okay? And using the standard equation for efficiency of a photodiode, we can back out the power conversion efficiency and see how efficient our materials are. Okay? All of the theory is the same in terms of power conversion efficiency as inorganic devices. However, how you generate that charge, how you conduct that charge, and the molecules you use in organic devices is very different. So what we'd like to do in our organic photovoltaics section of the course is to describe the transport differences and the nanostructural characterization differences between inorganic devices and organic devices. The third example in the course that we'll talk about is thermoelectric materials. Now, as we know, a thermoelectric material is one where we have a hot side of the device and a cold side of the device. And this temperature gradient between hot and cold allows for the flow of charge between the hot side to the cold side. Okay? So this thermal gradient allows us to convert waste heat energy into electrical energy. Okay? And the way we measure how efficiently we do this is through something called the figure of merit. And the figure of merit has three key properties. The first one is the electrical conductivity of the materials. The second is the Seebeck coefficient, or the amount of voltage that's received per unit change in temperature, and the thermal conductivity. Now, as you might imagine, you want to keep the thermal conductivity low so that the hot side stays hot and the cold side stays cold. Obviously, you want to get that charge out as quickly as possible, so you want a high electrical conductivity, and the higher Seebeck coefficient you have is also a benefit as well. Now, in traditional inorganic materials, there's a trade-off between electrical conductivity and the Seebeck coefficient. And in fact, as you dope a material, you will increase its electronic conductivity, but you'll decrease its Seebeck coefficient. Therefore, the numerator in this equation ends up having a peak of S squared times sigma. In organic materials, this necessarily is not the case. Okay? The theory that supports this and the theory that's derived for this may or may not apply to polymers. This is very in-depth and undergoing research, but it seems as though the paradigm of this maximum in S squared sigma does not apply to polymer semiconductors. So we'll explore why that is and how we can use that in devices that gather waste heat and convert it into useful electrical energy. Okay. Those have been 3 key examples of applications that we hope to explain organic semiconductors in. Okay. We'll cover in this course the fundamentals of the materials design. We'll cover how transport is performed in organic electronic materials, and we'll cover how that transport then can be affected in different devices and how we can tune the materials to have optimized device performance for different devices. So what are we going to cover exactly in this course? Well, the first thing we'll cover is the molecular properties of organic semiconductors and how these can be tuned to change the electronic properties. Second, we'll talk about how to characterize the molecular properties and the nanostructural properties of these materials in a way that allows us to understand how to relate the nanostructure to the ultimate device performance. Thirdly, we'll differentiate between charge transport in organic materials versus inorganic materials and how this can benefit researchers in certain applications. Finally, we'll talk about how to implement these materials in functional organic electronic devices. As you can see, this covers a wide range of disciplines. It goes all the way from polymer science and chemistry through materials design, chemical engineering, electrical engineering, device physics, and device modules. As such, this type of material is very rarely covered in the traditional university setting. Here we've set up a one-stop course that allows us to have a flavor of each one of these types of avenues and provide a broad perspective of organic electronic devices such that you can be well prepared to find these out in the real world. So who should take this course? If you are an undergraduate student interested in chemistry, physics, chemical engineering, material science, or electrical engineering, this course will have something to provide you a flavor for all of these fields. And it'll let you implement your background and knowledge such that you can begin to think about organic electronic devices. If you are a grad student researching polymers, organic electronic materials, or organic electronic devices, this course will allow you to dig deeper into the literature and allow you to bring yourself up to the current state of the art in a variety of fields. If you're an industrial professional who's been thinking about working with organic electronic materials or devices, or taking an entrepreneurial spirit in the field, this will give you the proper background so that you can make executive decisions in a manner that is consistent with the proper economics and scientific background. So what I hope I've shown you today is that organic electronic materials and devices are interesting, they're fun, and that they're very relevant to the emerging markets in today's society. With that, I'll remind you that registration for the course is now open, and if you visit this website, you can sign up very quickly and efficiently. With that, I thank you for your time, and I hope to see you online in the fall.